Modern complex systems, from autonomous vehicles to aerospace platforms, are rarely engineered as single products. Organizations must produce tens of thousands of variants simultaneously. Historically, engineers managed this variation through a method known as clone and own. When a new product variant is needed, they copy an existing product's assets, modify the necessary code or CAD files, and save the result as a completely independent project. This approach fractures the engineering ecosystem into disconnected silos. A security patch or hardware update applied to a core component must now be manually tracked and replicated across thousands of isolated variants. The resulting technical debt compounds exponentially, eroding the underlying architecture and driving maintenance costs to unsustainable levels. To solve this, the industry developed Software and Systems Product Line Engineering, or SSPL. SSPL proposes treating the entire product line as a single consolidated asset base, rather than a collection of standalone projects. However, while SSPL provides the conceptual framework, executing it across massive engineering pipelines requires highly automated tools governed by strict mathematical rules. That execution model is defined by ISO IEC 26580. This international standard dictates the exact technology layer required to build a feature-based PLE factory, a highly automated environment that generates product variants without manual intervention. Continuing with the clone and own method guarantees eventual architecture collapse. Surviving enterprise scale requires transitioning away from manual duplication and adopting the rigid mathematical factory model outlined by ISO 26580. A major hurdle in adopting a unified engineering factory is the reality of the modern toolchain. Systems rely on highly heterogeneous tools, like mechanical CAD modeling files, complex electrical circuit schematics, SysML system architecture frameworks, and diverse software development environments. Forcing an organization to rip out these specialized tools and consolidate into a single proprietary ecosystem would incur impossible transition costs and severe vendor lock-in. To prevent this, ISO 26580 operates on a strict black box implementation independence principle. The central PLE factory dictates the rules of variation, while connecting to external domain tools via standard interfaces. The standard rigorously defines the required inputs, outputs, and behaviors of the factory, but it remains completely neutral on the internal algorithms, processing logic, or specific database schemas used by the tool vendors. This open attachment structure allows legacy engineering tools to plug directly into the PLE factory. They operate under a unified logic without requiring replacement. By mandating implementation independence, the standard protects decades of legacy enterprise tooling investments while establishing a unified single source of truth for the entire product line. The engine that drives this factory is the feature language, a four-part semantic model that translates abstract product choices into physical engineering assets. This diagram represents the first layer, the data declaration language. This language maps the 150% model, the absolute superset of every possible feature and alternative that exists across the entire product family. It uses specific structural syntax to bound variability. For example, a simple optional feature allows engineers to define a straightforward binary choice. A capability is either included in the final product or it is not. Conversely, a mutually exclusive choice forces a strict selection of only one alternative from a set. This defines critical hardware architecture branches where two physical states, like a gasoline engine and a fully electric drivetrain, physically cannot coexist in the same vehicle. For non-functional attributes, the standard provides a scalar choice mechanism. This allows the system to assign a specific numerical range or text string, like a sensor calibration value, directly to a parameter. ISO 26580 outlines 6 of these distinct choice types, and together they dictate the absolute boundaries of what downstream engineers are allowed to design. The data declaration language acts as a mathematical fence. It formally eliminates rogue, unapproved variants before they can ever reach the engineering phase. In a massive catalog containing thousands of features, these choices do not exist in a vacuum. They are highly interdependent. This introduces the second layer, the feature constraint language. It formalizes the logical, physical, and regulatory dependencies between features across the entire system. It utilizes n-ary Boolean expressions to enforce complex rules. For instance, if an autonomous driving feature is selected, the logic dictates that it explicitly requires a specific LiDAR sensor and a redundant braking system to be valid. The standard requires back-end SAT or SMT solvers to instantaneously evaluate these complex Boolean constraints in real time whenever a feature is selected. This solver mechanism actively prevents combinatorial explosions, shutting down pathways that would allow conflicting physical components to make it into the final design. With tens of thousands of potential variables, identifying every conflicting feature manually is mathematically impossible. Machine-evaluated constraints ensure the configuration is flawlessly valid before a single physical asset is generated. Once the configuration is validated, we reach the third layer, the data instantiation language. This is the process of locking in those valid choices to create a 100% bill of features, or BOM. This BOM is the precise blueprint for a single specific product variant. But how does an abstract, logical BOM actually alter the physical lines of C++ code, mechanical CAD files, and system models? That translation occurs in the final layer, the variation point language. This semantic spec maps the chosen features directly to the precise locations inside the physical engineering assets that need to change. In legacy environments, variability logic is heavily siloed. Software teams use preprocessor macros, hardware teams use massive spreadsheets, and requirements teams use proprietary metadata tags. ISO 26580 replaces this with universal rules. Under the inclusion-omission semantic rule, a block of code, a CAD component, or a SysML node is simply included in the final output or stripped away entirely, dictated solely by the BOM. It also supports dynamic mechanisms like the generation rule, where the configuration actively injects specific scalar values, such as a dynamically calculated buffer size, straight into the code right before compilation. Implementing a single variation point language eliminates domain-specific silos. Hardware, software, and requirements teams are now forced to obey the exact same semantic rules of variability. The components are finally handed to the PLE Factory Configurator. This is the automated assembly engine that takes the specific BOM and the 150% superset and executes the physical generation of the final product. The configurator operates as a precise structural parser. It manipulates the internal relationships of the files themselves, moving beyond simple conditional file duplication to ensure structural integrity across the variant. This parsing capability is critical for safety-critical domains like automotive and aerospace. In these industries, stringent regulatory audits mandate unbroken traceability links, proving that every software requirement maps directly to a corresponding test case. The configurator executes traceability transformation. A requirement node maps to a test case within the superset web. If a variant omits a feature, the requirement drops out. The remaining connection to the test case becomes an orphaned, broken link, instantly failing a safety audit. The configurator actively hunts these logical contradictions during assembly. It removes the broken links, purges the orphan test cases that no longer serve a purpose, and cleanly reroutes the surrounding network. This dynamic adjustment guarantees that the resulting 100% product asset is perfectly whole, structurally sound, and ready for immediate verification and validation. Traceability transformation eliminates the massive manual overhead of regulatory compliance. It guarantees every generated product variant satisfies rigorous audits the moment it is compiled, without any human intervention. Deploying this factory architecture across an enterprise means hundreds of engineers will be accessing and modifying the 150% superset concurrently. Over years of development, the greatest threat to a product line is architectural evolution. The 150% catalog structure will inevitably change. A feature that was once a simple optional toggle might be expanded into 3 mutually exclusive hardware branches. When that happens, thousands of older product BOMs will instantly mismatch the new catalog schema. To survive this, ISO 26580 dictates a requirement for consistency migration. The environment must analyze structural changes to the catalog and automatically realign thousands of historical BOMs to the new schema without losing data. Furthermore, the standard requires open APIs and command line interface integration. This pulls the PLE Factory out of an isolated desktop application and embeds it directly into the enterprise's automated CI/CD build pipelines. ISO 26580 provides the definitive blueprint for transitioning an engineering enterprise from single project development into an automated, mathematically verified factory. It enables the mass customization of complex systems while maintaining architectural integrity through every generation.